Okay, let's talk about models some more. So one of the things I want to point out to people, and you tell me what you think about this, is that it is perfectly possible to produce pretty damn good computer models that predict the behavior of the stock market in the past. And the stock market's very complex, of course, because it's an index of, well, the sum total of human economic activity plus political activity. So it's a very dynamic system, and it's full of weird feedback loops because as soon as you can predict it, you perturb the system. But in any case, here's the fundamental point. It doesn't appear to me at all that the stock market is more complex than the climate. And if you could produce a model that could predict the climate, then you could produce a model that would predict the stock market. And if you could produce that model, even if you only were right 51% of the time, consistently, you would soon have all the money. And I don't see anybody who's developing these very complex models who has all the money. So I don't think that they can make models that can model the behavior of systems that complex. And so let's talk about models a bit.
So let's talk about models a little bit. Let me back up again and talk about some of the basics. The most used models for the climate system are what are called general circulation models. They cut the atmosphere and the ocean up into cubes, about 100 kilometers on a side, 60 miles on a side, and going up 20 layers in the atmosphere and then 20 layers down in the ocean. And we have a difference to the stock market is we have some underlying physical laws. The laws of conservation of energy, mass, momentum, and so on, that govern how the air, the radiation, both sunlight and heat radiation, water vapor, flow through these boxes. Newton understood those, or Euler, back in the 19th century or even earlier. And we can build such models and use computers. So you wind up with I've ordered 10 million boxes covering the Earth, going up and down in the ocean, the atmosphere. And then you follow the flow of stuff through these boxes every 10 minutes, 10-minute time steps. And you do that for a century or so, and you got some description of what you think is the climate. But there are lots of problems with that. One is that 60 miles on a side is not sufficient to describe the difference in climate between New York and Washington, D.C., or New York and Toronto, for example. So that's one. And so the second is a lot of phenomena happen on much smaller sizes. Think about thunderheads, for example. Okay, they happen on a few mile scale. So you have to make up some assumption about what's going on inside each of these boxes. And different people make different assumptions. A third is that the boxes are not really cubes, but they're pancakes because the atmosphere is really thin compared to the size of the Earth, and the ocean is also pretty thin. And so you have to make up assumptions about how things move vertically that are not directly tied to the fundamental physical laws. So all of those, make a lot of trouble. And that's why the world has 50 different such models. And to get predictions, they average all of them together.
Okay, so let's take that apart just so everyone understands. So the first is these models are not very high resolution, either spatially or temporally. So you have to use huge cubes, plus you're only sampling...
Temporally is pretty good, 10 minutes. Spatially,
right, but
it's terrible.
But we also, perhaps on the temporal side, the thing is we're looking at relatively small deviations in temperature, right? If it's 1 degree over a century, this is not a huge effect. And what that means is that the models aren't high resolution enough to be accurate to that scale. They're simply not.
That's true. That's true.
Now, that doesn't mean we shouldn't model, because our models get better and better all the time. But there's a big difference between modeling something, even if you can make it accurate to predict the past, and being able to model the present. But there's a walloping difference between being able to model the present and being able to model climate 100 years from now, because the errors compound as you predict out into the future.
Yes, that's certainly true, although you hope to be describing averages that are reasonably well predicted. There's several comments about that. One is, on human influences are small. They're, as you say, a 1% effect. We're concerned about a rise of 2 degrees, whereas the Earth's surface temperature is about 300 degrees, so it's like a 1% effect. The second is, we're interested not in describing the climate, but in describing how the climate responds to those influences. That's the big question. And that's an order of magnitude harder job than describing the climate itself. The third thing is, we're looking over timescales of 100, 150 years, and we have terrible data to describe what happened in the past. Yes, we have reasonable confidence about the average global temperature, but what goes on in the oceans, which is really where climate happens, the oceans are the long-term component of the system, we have terrible data until about 20 years ago when we started putting out floats of various kinds.
Well, and how good is the ocean data? I mean, the ocean's pretty damn deep, and it's not like we can measure everything that's happening in the ocean. I can't imagine we understand long-term current flows from the depths well enough to be predicting climate alteration on the scale of a few degrees. That just strikes me as unbelievably preposterous.
Right. Studies that have attempted to reproduce the warming of the ocean show that the ocean was warming at about half the current rate, even as the Little Ice Age started to end. And so untangling this long-term natural variability from the effect of human influence, which has only really been significant for the last 70 or 80 years or so, is a very, very difficult problem, maybe the central problem in climate.